High-performance SAR ADCs can offer amazing dynamic range and linearity at faster and faster sample rates. But how do you design the amplifier and interface at the analog inputs? LTspice can help. Welcome to the LTspice IV SAR ADC driver video. I am your host, Chris Loker. This video shows how to use LTspice to simulate the analog input interface of high-performance SAR ADCs. We will look at charge kickback, settling time and noise, and how to make trade-offs between sometimes conflicting goals. The SAR ADC family used in the examples that follow are the LTC2378 family, which offers sample rates from 250 kilosample per second to 2 megasample per second and resolutions from 16-bit to 20-bit. This is a great ADC to learn how to use because it offers up to 104 dB signal-to-noise ratio and the highest linearity in the industry. Here I'm showing how to build a model for the ADC analog input. The datasheet says that there are 40 picofarad sample capacitors which periodically get connected to the inputs and disconnected again. So I have the 40 picofarad capacitors and I insert voltage controlled switches between the sample capacitors and the analog inputs. I create a model name for the switches. In this case I just call it my switch. In the model statement I say that the on resistance is 40 ohm, that comes from the datasheet, and a logic threshold voltage of 0.5. If the control input is higher than 0.5, the switch is on. If the control input is lower than 0.5, the switch is off. Now I create a logic signal using a voltage source with the keyword pulse. I let the signal have a period of 1 microsecond, which corresponds to a 1 megasample per second sample rate for the ADC. I let the signal be high for 330 nanoseconds, which is the acquisition time of the ADC. This is the time during which the sample cap is connected to the analog input. The pulse is low for the remaining 670 nanoseconds of the period. This is the conversion time of the ADC, during which the sample cap is not connected to the analog input, but instead used by the ADC to determine the digital output codes. Note that I also insert an inverter to create the opposite phase of the clock, and this controls a second set of switches. These switches are responsible for shorting out the sample cap during the conversion phase. This way, every time that the sample caps get reconnected to the inputs, they start with 0 volts across them. Notice one important thing about this ADC. The inputs are differential, and as you can see from the sine wave drawings here, that means that the ADC expects a signal to come in this balanced way. It means that whenever in plus goes high, it wants in minus to go low. It wants the instantaneous average or common mode of the input signal to stay at half the full scale voltage, in this case 2.5 volt. So now let's look at the LTspice schematic of a circuit to do that. Here I have the LTC6362 differential op-amp with 4 feedback resistors wrapped around it, just as shown on that component's datasheet. The circuit is powered from a single 5 volt supply. I short one of the resistor inputs to ground, and at the other input I connect a sine wave, which is centered on ground with a 4 volt amplitude. When I run the transient simulation, I see that while there is just one input, which swings above and below ground, there are 2 outputs, out P and out N, and they swing differentially with respect to each other. They are a mirror image of each other. So the op-amp creates the desired property for the inputs that should go into the differential ADC, since whenever out P goes high, out N goes low at the same time. Also notice that the average of the 2 outputs stays put at 2.5 volt. That's controlled by the voltage on this VOCM pin, which for this amplifier defaults to 2.5 volt, though we could also overdrive it to some other voltage if needed. Next we're going to put the amplifier and the ADC together into one schematic. In this schematic I have literally copied and pasted the previous 2 sections together. Notice the differential op-amp circuit here on the left and the ADC input model on the right. Also notice that in between the amplifier and the ADC we place some series resistor and parallel capacitors. I will run a transient simulation of 1 millisecond, which is one period of the input sine wave of 1 kHz. Meanwhile, the ADC clock still runs at 1 MHz, so there will be 1000 samples taken as the input signal transitions through one input signal period. Now we can look at some interesting things that will give us insight into what goes on at this interface between the amplifier and the ADC. As I plot the analog inputs into the ADC, I see the expected voltage sine waves, with each node here swinging between 0.5 volt and 4.5 volt. Now I'm also going to plot the current coming out of the sample switches. This is the dynamic load that the ADC places on the driving network. We see this current waveform. Because the sample capacitors always are discharged to 0 volt before being reconnected to the inputs, and the input signal is not 0 volt, every time that the input switches gets closed, there are these immediate spikes of current being drawn through the switches to charge the sample caps. What we see in this waveform is that sometimes the current spikes are 0. This is when the two inputs are equal to each other at 2.5 volt, because then there is no voltage difference between the inputs and the discharged sample capacitors. But when the inputs are at 4.5 volt and 0.5 volt respectively, this is 2 volts away from the midpoint of 2.5 volt, you get current spikes of up to 50 milliamps, which is equal to this 2 volt difference divided by the 40 ohm on resistance of the sample switch. If I zoom in the time axis onto those sampling events, I can illustrate a little closer what's happening. Here I see the brief current spikes coming through the sampling switches, and I also see the internal sample cap nodes transitioning between these discharged states at 2.5 volt and the actual input voltages of 0.5 volt and 4.5 volt. It's important to realize that the voltage which the ADC will try to convert to digital is whatever voltage is present across the sample capacitors right at the time that the sample capacitors will be disconnected from the inputs. So we should zoom in on that area and see whether these sample capacitors actually fully charge up to the final value. To check the settling of the sample capacitors, I plot the differential voltage across the capacitors V ADCP, ADCM, and I compare that to the circuit's input voltage Vin. Ideally, at the end of each acquisition time, the sampled voltage is equal to the input voltage. So when we zoom in on that region, we see that it takes quite a while to fully settle all the way from 4 volt down to the microvolt level. And note that an ADC of 16, 18 or 20-bit resolution has LSBs on the order of 100 microvolts. In this example, we actually see that the capacitor value has not yet fully settled to the microvolt level at the end of the period. And we can derive that this is because the 1 nanofarad external capacitors in the circuit take a while to settle through the series 20 ohm resistors. So if, for example, I reduce these capacitors from 1 nanofarad to 470 picofarad, which I do here using the step param command so that I can do a side-by-side comparison, then I see that with the smaller capacitor value, which is the blue curve here, the curve settles faster, as expected. If this were everything, it would be easy. We just reduce the capacitor to make the settling faster and we would be finished. But as usual in engineering, there are trade-offs. To understand what that trade-off is here, let's look at noise. To study the noise of the circuit, I keep exactly the same schematic, but I replace the transient command by a noise simulation command. I define the noise output as the differential signal at the input to the ADC and sweep the noise analysis across frequency. Then I can plot output noise by selecting VO noise. Note that here I am also still stepping the filter capacitor value, so I actually get two noise curves. The simulation with the smaller capacitor value, which is the blue curve, extends the noise density to higher frequencies, which means that the total integrated noise will be higher. To look at the integrated noise, I have to turn off the step param and choose just one cap value at a time, and then run the noise simulation again. If I then plot the output noise and press Ctrl plus left mouse button while hovering over the label, LTspice calculates the integrated noise for me, which is in this example 42 microvolts RMS. I can then use this to go back and change the cap to find a good trade-off between noise and settling time. I can also look at which components in the circuit cause most of the noise, such as op-amp noise or resistor noise. There is much more to say about simulating SAR ADC driver interfaces, and there are also some aspects such as linearity which cannot be easily simulated. Nevertheless, the LTspice analysis that we just discussed provide great insight into the behavior of the interface between an amplifier and a SAR ADC, and they can be a useful tool to make the right engineering trade-offs. For more information or to download LTspice for free, please visit us at www.linear.com/LTspice.